roots, fourth roots, etc., nth roots. And we're going to really just take a look at the rules that are related to radicals, and we're going to see that there's a correlation to those rules to something we've seen before. Okay, so we're going to take a look at expressions that we want to simplify. Okay, so he knows, and he reset it this morning and said, let me know how it works. I'll let him know that it didn't work, whatever he did. Okay, so we summarize that rule while there's no sound there. But remember, it's the nth root. So square root, cube root, they all hold true. An example, look at part A. Clearly, this is not an example of what we just saw, but I can make it look like that. How can I make 75 look like the product of two numbers? What would work out really conveniently for me if I made 75 into what two numbers? What two numbers could I write 75 as? A very simple answer.
25 and 3.
25 and 3. I mean, 75 has very few factors as it is, right? It's 5 and 15, 25 and 3, or 1 and 75. Those are the only integer factors. Obviously, all the negatives apply as well. But it makes sense to use 25 and 3. Why, Morgan?
Because 25 is a perfect square.
25 is really a perfect square, and thus, as a result, we can take its square root. So this simply becomes 5 root 3. Rule of thumb, very simple. Put the perfect square out front. Put the perfect square first, or out front. So when you reduce it, you end up with a coefficient of 5. Is that clear? Please don't write it as radical 3 times 5. Because then you don't know, is the 5 underneath the radical? Is it 35? Is it outside? Tradition, and you're going to see it everywhere, is that you have an integer value multiplied by a radical value. You always see the integer first. So 5 root 3, not root 3 times 5. Okay, so again, take the perfect square and put it first. List the perfect square first, then list the non-perfect square, so that when this reduces, it ends up out in front. Part B, can I break up 8 and 6 into perfect squares? Sure, I could break up 8 into 4 and 2. Right, I could break up 8 into 4 and 2, but 6 doesn't get broken up. This may be one of those times where it might be actually useful to multiply it first. What's 6 times 8? What's 6 times 8? 48. Can I break 40? So I'm going to multiply it out first, right? I'm going to first multiply it, actually. Then I'll bring it back up. Can I break up 48 into two factors, of which one is a perfect square? And I want that perfect square to be as large as possible. As large as possible. 16 and 3. Now, it's very tempting to say 4 and 12. So let's go through this. For this one, for this one here, this is really what it is. So I could say, all right, let me use 4 times 12, keep the negative sign out front, or, as Morgan said, 16 times 3. Which of these options is better? Well, the second one is definitely better. Why? Question or answer? Good.
So the second one is better because you can just take the root. But in the first one, you could do it too because 12 is really root 3 and root 4. You just take the root of 4 and the other 4 and multiply it times.
So what Inigo's noticing is that you have root 4 times root 4. Isn't that just root 16? That's where this comes from right here. And then the root 3 that was here is really here. So either way works, right? That's what you're getting at? Either way works, but one is more direct than the other. The one that's more direct is the larger of the two perfect squares. This simply reduces to be negative 4 root 3. Well, you know what? This becomes root 4 times root 4, which is just 4. And then the root 3, and then this negative sign here we can't forget about. So either way, we get the same answer. Negative 4 root 3. Now, if I hadn't multiplied it to start and to get 48, I could have broken up radical 8 into 4 times radical 2. So there's a third way to do this problem. Let's go through that. I want you to see all the options so that you can recognize which is the best. Take this and break up the radical 8 to start into radical 4 times radical 2. And what's radical 6 really? What's radical 6?
Oh, 3 and 2?
Yeah, it's really 3 and 2. Well, what you're going to notice now is that you have radical 2 twice. What's radical 2 times radical 2? Radical 4. And radical 4 is actually 2. So if I multiply these two things right here, I'm going to get root 4. And root 4 is really 2. And I have another 2 out in front because this root 4 gives me a 2. And then this root 3 carries down. So again, these two together gave me that right there. And then the root 4 came down as a 2, carried down the negative sign, which gets me back to negative 4 root 3. Again, the same answer in every scenario. So what I'm getting at is this. It doesn't really matter which method you take. If you want to multiply it out first, if you don't find the largest perfect square. But if you don't find the largest perfect square, you should know that the result can still be broken down further. Okay? Until you factor it into its largest perfect square, you're actually not simplified completely. So make sure to look for that largest perfect square to help you. Part C was the cube root of 25 times the cube root of 10. Now, we got to pause for a second, because we haven't even gotten to cube roots, right? How's a cube root going to work? For a square root, I look for a perfect square. For a cube root, a perfect cube. What about perfect cubes? Can anybody list at least the first 5 perfect cubes? The first 5 perfect cubes? 1 cubed is? 2? 8. 3? Cubed. 27. 4 cubed?
64.
5 cubed?
125.
6 cubed?
158.
216? 7 cubed? 343? Good check. I think they're really. What I'm getting at is at that point it doesn't matter, right? Clearly, I'm trying to figure out myself. So you should know like 1 through 5, right? Okay? 1, 8, 27, 64, 125. Now, knowing those numbers, look what we have here. Is 1 going to go into these short? That doesn't help you. Does 8 go into 25 or 10? No. Does 27? No. Does 64? Sure doesn't. 125? Doesn't either. But what can I do if nothing goes into those two numbers separately? What do we do in part B? Yeah, Jeff. Yeah, start by multiplying them first. So let's rewrite this. What's root 25 times, cube root 25 times cube root 10 is cube root 250, really. That's what that is. That law that we wrote on the second slide told us that we could break something down. So we can put it back together also if we can break it down. But now we're going to re-break it. We put it together, and now we're going to break it apart. But what should I break 250 into that would make more sense than 25 and 10? What perfect cube goes into 250? 75. 75 is in a perfect cube. Remember, look at your perfect cubes. You got 1, and Alex,
125.
And
2.
And 2. 125 is a perfect cube, right? Isn't it 5 cubed? 125 is 5 cubed. So let's break this into 125 times 2. So here's what you do. Put your cubes on the side if you need to. Write them over here, please. And you really only need to know the first 5. After that, you're not going to really do much with this. And just look at those 5 and ask yourself which of these 5 goes into 250. Because it's a cube root, so we're looking at perfect cubes. And 125 goes into that. So we break it up like this. The perfect cube first, like earlier, and then the non-perfect cube after. Remembering to put the little 3 for the index on both radicals. And the cube root of 125 is indeed 5. So this can be reduced to 5 times the cube root of 2. So what we're doing is simply reducing our radical. Okay? We're breaking our radical up into numbers that just work a lot easier for us. Okay? We're factoring here. We're factoring. Try the last one, part D on your own. Try part D. It's going to be a little bit tricky. Root 120 over root 10. Root 120 over root 10. And there's definitely 2 ways to do this. You could choose either way. It's up to you. Both will work. One will be faster than the other. Give me one way to do it, please. Give me one way, Jeff.
Break down root 120 into root 12 and root 10. And you can cancel the out of root 10.
Yeah, definitely start by doing that, right? Do we all see that? So reduce. 120 over 10 is really 12. So reduce this to radical 12. And then, Jeff?
And then it becomes root 4 and root 3, which is 2 times root 3.
Okay, that's definitely the most direct route. It's not the only way to do it, but this is the most direct route for sure. Yeah.
Wouldn't a slightly more direct route just be to divide first? And
That is what he did, though. Yes, that's exactly right. You're saying, just look at this. 120 over 10 is 12, isn't it? And just write that down and skip this factor. You could skip that factor, yeah. But in theory, by factoring and canceling, isn't that what you're doing by reducing? Division is defined as taking the factors that are common and canceling them, really. That's what you're doing by division. Yeah. The way that's not the most direct route that I was hoping people wouldn't do would be to break up 10 into 5 times 2, break up 120 into like 4 times 30 and try to go that route. That would be a very indirect route, which would work, but it would take you many extra steps. So yes, either factoring, dropping the 10s, or as Amigo said, right, look, these both have zeros, this becomes just 12 over 1, or just radical 12. So you can jump right there. You don't need what's in red here if you want. Okay? So the idea, factor, reduce. Preferably factor into a perfect root. Perfect square, perfect cube, perfect fourth, dependent upon what the index is. If I'm taking a cube root, I look for perfect cubes. If I'm taking a square root, I look for perfect squares. If you're taking a fourth root, you want to look for perfect fourths. I'm not going to go crazy with them though. But the first couple you can know. 2 to the fourth is 16. 3 to the fourth is 81. 4 to the fourth is going to be 256. 5 to the fourth, 625, I think. But you're not going to have to know much more. So if you know the beginning of each, or if you have a calculator, just check into what they are and go ahead and divide them into the radicand, so you can see. And go a lot further with it. And let's take that concept and relate it to how we're going to look at variables now. Okay, how are we going to look at variables? So let's first start by looking at part A. I've got the square root of 3ab squared. Well, clearly I cannot break 3 into factors. 3 and 1, great. That doesn't do me any good, right? No perfect squares. A is not a perfect square. Is b squared a perfect square? It sure is. It better be, right? If it's a square, it is a perfect square. So what I would do to start part A is break this into radical b squared times radical 3a. The second slide of our notes told me that this is allowable. I can take a product and break it into the square roots separately in that product. And I could take the square of a product and make it the product of square roots. Well, what's the square root of 3a? You can't do anything with that. That's going to stay the way it is. Radical 3a is still radical 3a. Radical b squared, believe it or not, well, we know b squared and radical, what happens to them? When you square a square root or square root of square, what happens? They cancel out. Now, that is true, but we have to point out that when you solve for something like this, you're actually assuming that you're looking for the principal square root. So when you write your answer down, you don't just write b times radical 3a, which one would think you would do. You put absolute value of b times radical 3a. Remember, we're not solving an equation. We're reducing an expression. And when we reduce an expression, we look for the principal square root. So if b squared, let's say b squared, that quantity had been 16, you would say the square root is just 4. You're not solving an equation where you say 4 or negative 4. So here, we're only looking at the principal square root, so it's the absolute value of b. It's kind of an annoying thing. I'm not going to go crazy. I probably won't even take all points if you forget to write it, because you don't see it too often. Okay, but just so you recognize that that's where that comes from. It does not apply for cube roots. The concept of absolute value is not necessary because cube roots, remember, they're either positive or negative. It depends on what you started with. How about part B? How about part B? What should I break that into? And remember, I need to break it into 2 roots here. Morgan.
Maybe square root of 49 is square root of 1, and then it's 7.
So no y in the first part, Morgan? Why?
This 49 is perfect square.
So is y squared, isn't it? So is y to the 4th. So is y to the 6th. Aren't those all perfect squares, actually?
Yeah.
So revise your answer.
49 y to the second and y to the third.
Revise it further. That's what you have right now. If you took out one set of y to the second, can't you take another y to the second out?
So that's times y to the square as well.
Yeah, so it's really like that, right? You see that? Think about it for a second, please. Isn't y squared a perfect square? And that occurs twice. You have y squared, and y. Why is that? Because y squared times y squared times y is y to the 5th. There are 5 y's listed there. And our idea is that we're taking all perfect squares out front. So reduce them all, please.
Can you just divide it into like 3 parts? That's like 49 and then y to the 4 and then times the radical of y.
Yeah, you could have done that. You could have done it this way. What Sarah's saying is just write it like this. And you were saying 3 parts, but I would just write it like this, Sarah, okay? But yeah, the 49 and the y to the 4th are both perfect squares. Well, what's the square root of y to the 4th? It's just y squared. Because this, if you recall, is really 7y, radical y. That's what that would become. So I'll do it the way Sarah said and take this and just say, well, this is just 7. The square root of y to the 4th is y squared times radical y. Now, I don't need the absolute value here. Why don't I need the absolute value? Why don't I need the absolute value here like I had earlier? Why is it only true for the square root? Square root of b squared earlier, we put absolute value of b. Why wouldn't I need an absolute value here? What happens when I square a number? When I square a number?
No, that becomes positive.
It's always positive. So no matter what I get here, this answer will indeed give me the principal square root. Okay, it will give me the principal square root. So we have 7y squared times the square root of y. It's the same thing as what's over here if we did them separately, because 7 times y is 7y squared. Okay, it is 7y squared. How about part C? The cube root of w to the 4th over y cubed. Cube root of w to the 4th over y cubed. What you got for me? Sarah?
If you divide w to the 4th into w to the 3rd times the square root of w. And then
Square root?
The, yeah,
Square root?
radical.
Cube root?
Oh, yeah, okay.
Right? Not square root.
Mhm. And then the bottom is just the cubed root of y to the 3rd. And then we can simplify those, so it would be like w times the cube root of w over y.
Yeah, so what Sarah's doing is she's recognizing that, what are you looking for here? You're looking for a perfect cube because you're looking for a cube root. Look at the index. The index is a 3. As soon as you see that the index is a 3, you need to break up your variables into something with an exponent that's a multiple of 3. So w to the 6th would work well here, w to the 9th, w to the 12th, w to the 15th, anything where the exponent is a multiple of the index. You want the exponent, again, the exponent to be a multiple of the index, always. So if this had been w to the 8th, I would have written it as w to the 6th times w squared, because 6 is a multiple of 3. If this had been w to the 13th, I would have written it as w to the 12th times w. So as many 3 w's or w to the 3rds you can get. Because the cube root of w cubed is just w. And the cube root of y cubed is just y. And then the cube root of w gets carried down. So again, this right here, this cube root that you're seeing, cancels with this cube. This cube root cancels with this cube. It always works out that way for perfect cubes and cube roots. Okay, for perfect cubes and cube roots. They always cancel each other. This one happened to be, I think, a little bit easier than what I had supposed as an example. before we get to part D, let me suppose what I was going to say, what I was actually getting toward there. Before we get to part D, write this one down, please. We'll go to part D in a moment. Let's write the following. The cube root of x to the 14th, y to the 12th. Or no, let's do y to the 9th. Y to the 9th, please. So I need perfect cubes because it's a cube root. The index is a 3. So look at your exponents. X to the 14th, I need to break that into two things. One of them needs to be a multiple of 3. One of them doesn't matter. So I break up first into my perfect cubes times my non-perfect cubes. How many x's can I put in the perfect spots? How many x's can go there? X to what power? Well, 12. We'll go over this if you're still a little bit lost. What does that leave behind for the non-perfect area? 2. Remember, if this was a square root, life would be a lot easier, right? This would be a simple answer. It would be x to the 7th. Right? The square root of x to the 7th, x to the 14th, would be x to the 7th. But here, I can't take the cube root of x squared. I gotta have at least x cubed for this to work. What's x to the 12th really? What's x to the 12th really? It's really x to the 4th cubed. So let me write that so you see that for those that are struggling with this. Think of this as x to the 4th cubed. Again, think of it as x to the 4th cubed. Then we have y to the 9th. We have y to the 9th. Isn't 9 a multiple of 3? So that means that it must be a perfect cube. Well, I'm just going to put all y to the 9th in here. James, what's y to the 9th as a cube?
Y to the 3rd.
Yeah, it's y to the 3rd cubed. Right? Isn't that really what it is? And look, it makes sense of your rules. That's why these rules are so important that you study. Look, 4 times 3 gives me 12. 3 times 3 gives me 9. So what did we say a moment ago? We said that a cube and a cube root cancel. So what I can do now is I could write my solution as simply x to the 4th, y cubed, times whatever's left over as the non-perfect, which I don't even care about, that extra piece. Remember, what we did here is the following. We canceled these cubes right here, I'm circling them. Those cubes cancel with this cube root, leaving me behind with what's in these boxes right here. X to the 4th, y to the 3rd. Again, you want to write your inside parts as perfect cubes. With numbers, this is so much easier, isn't it? Because it's like, oh, you know what? Under a cube, I'm going to put the cube root of 8, and that's just 2. Or the cube root of 27, I'll put out here, and that's just 3. But when you get to variables, it becomes a little tricky. So if you remember just to take the exponent and divide it by the index. 12 divided by 3 gives me 4. Okay, take the exponent. Simple rule. Take the exponent, divide it by the index, you will get this expression. Take the exponent, divide it by the index, you will get what is here always. And that's because of this rule. You can divide this by this because this is really factoring. Factoring is like dividing. Okay? So that would be your solution for that extra problem I just threw in there. Let's look at the last two parts now. We've got part D, which says the following. The square root of 9w squared plus 9u squared. Ooh, this is a tempting one to make a common mistake. Make that mistake that I warned you of in the beginning. What would the mistake be here? Don't tell me the answer. Tell me what the mistake would be. Inigo?
To just take 9w out
And what else?
and 9u out.
Yeah, to do them separately, right? To literally evaluate them separately. But you can't do that. Why not? You're adding. Remember, this doesn't hold true for adding and subtracting. So, I need some sort of a multiplication, don't I? What can I factor out of both of these terms? 9. And then write it like this. Now, don't I have multiplication? Jeff, where's the multiplication sign?
Between 9 and the quantity of the square.
Yeah, between 9 and that quantity that's there. So, you know what? Write it like this. We know from that rule from the second slide of our notes, we can do this. We can break it into the product of two radicals instead of the radical of a product. And the square root of 9 is simply 3. That's all you can do. You cannot go further because you still have a sum. The sum is w squared plus u squared. And the last one, we've got the square root. I'll put it on the right in case people are still copying that. We've got the square root of x squared plus 12x plus 36. Well, clearly here, this is asking me to make mistakes, right? It's like saying, oh, can't do anything because it's a plus. But earlier, when we had a number like the square root of 75, we broke it into 25 times 3. We broke it into factors. So we factored a number. Well, now it's an expression. Why don't you go ahead and try to factor that expression? Go ahead and factor that expression. Will, what do you get?
X plus 6 and x plus 6.
It's the same expression twice. So as a result, I could write it like this, can't I? Isn't that what that means? And don't a square root and a square cancel each other? So as a result, we get x plus 6. And remember, when it's a square root of a square, we put the absolute value around it. When it's the square root of a square, well, so in one instance, we're going to do that. We put the absolute value around it. Okay? Again, square root of a square cancel, but we need that absolute value there. All right, 2/3 of the way done. The next part is actually not too difficult, but we have to go through a test. So this process itself is not as necessary as it used to be. And part of your homework, I'm going to ask you to read, and you'll understand why I want you to read. And there used to be a time where with calculators, we would have trouble evaluating things. Now we don't have as much of a problem. So this process is not as useful with numbers, but it comes up a lot with algebraic proofs and some stuff you're going to discuss in your pre-calc and calc classes where you need denominators that are rational. So this is called rationalizing the denominator. And the whole concept is this. If the denominator has a radical in it, get rid of it. So if I have square root of 2 in the denominator, or square root of 2, that's not very useful. I can't take the square root of it. But if I can make it square root 4 somehow, that becomes just simply 2. So we're going to talk about how to get rid of that radical in the denominator that we do not want. Okay, part of your reading, you're going to have to read like a half a page that I ask you to read. Okay, it'll explain why. So look at the first one. Look at part A. Radical 7/3 is really radical 7 over radical 3. But I don't want a radical in the bottom. That's the whole idea of rationalizing a denominator. Rationalization of a denominator states there cannot be a radical in the denominator. So, radical 3, is that a perfect square? No, clearly not. But I can multiply 3 by something to make it a perfect square. What number should I multiply 3 by to make it a perfect square? 3. So why don't we do that to the top and bottom? Why am I allowed to mathematically do what I just wrote in red? What's root 3 over root 3? Everybody. I can multiply anything by 1, right? And it's still the same thing. Which makes the top what? Radical 21, doesn't it? And it makes the bottom, what's root 3 times root 3? It's just root 9, which is 3. So that would be considered a rational, not irrational, a rational denominator. Rationalization of a denominator indicates that you need to get the denominator to become a perfect square or a perfect cube or something like that so that it becomes a rational denominator. How about part B? This is really root 3 over root A. What should I multiply by to get rid of that root A in the bottom? I don't want a root there.
Multiply by root A.
Over?
Over root A.
Yeah, multiply by root A over root A. Which makes the denominator, or the numerator, root 3A, the denominator, root A squared, which tells me it's just going to be root 3A over absolute value A. Okay, it's just going to be root 3a over the absolute value of a there. Part C. Look at part C, please. This is a little bit difficult. Please don't pack up yet. Look at part C. We've got the fifth root of c over the fifth root of c squared. Well, how can I get rid of a fifth root if I have a perfect fifth? I need to have a perfect fifth to get rid of a fifth root. So what should I multiply the top and bottom by? The fifth root of what over the fifth root of what? Intuition here might help you. Will, what do you got? C cubed. Let's go over why he said c cubed. C cubed in the bottom, give me one sec, makes the numerator c to the fourth, which is fine, but it makes the denominator the fifth root of c to the fifth. Look at the denominator. It's now a perfect fifth, which means our answer becomes the fifth root of c to the fourth over c. So the whole goal of rationalization of a denominator is to make whatever the index is a perfect of whatever that is. So a perfect fifth, a perfect sixth, a perfect seventh, etc. Tonight you have homework, okay? Make sure to get to it. There was one more example. You're welcome to look at it if you'd like to. It looks like a lot. It's not a lot. I know, it looks like a lot. The reading is very short, and the problems do not take you very long at all.